So this problem is similar to the problem 4 he has asked you on the group homework. So here it is. I'm going to read it. Anthropologists use a linear model that relates human femur length to the human's height. The model allows anthropologists to estimate the height of an individual when only a partial skeleton is found. Below is data for 8 individuals. So so here's the data, the femur length versus the height in centimeters. And they want us to make a scatter plot. And so this is something you can totally use Desmos for. Which I already actually had up, but fine.
All right, where can we find that?
The question?
Yeah.
So if you go to the link I just sent you and click on this first one here, and then scroll down.
There. Oh, okay. Thank you.
Okay. So what we're going to do is we're going to use Desmos to make a scatter plot. Let's scooch this over here. Yeah. God. I need a bigger monitor. I mean, the monitor's pretty big, but it could be bigger. So let's go to actually the graphing calculator. And I want to make a table, so I'm going to click on the little plus sign up here and make a table. And then I'm going to enter the x's. So the easiest way I found to do it is to enter your x and then hit enter, because it'll take you down to the next one. So let's enter all the x's first. So 50.1, 48.3, 45.2. You can probably also do some copying and pasting if things are set up that way. Whoops, I missed the 0.5 there. Let's go back. 42.7, 39.5, and 38.0. And then for the y's, we have 178.5, 173.6, 164.8, 163.7. I probably could have done this ahead of time. 168.3, 165.0, 155.4, and finally 155.8. Okay, and then if we zoom out to an appropriate range and domain, so I want to be between 30 and 40 for the x's, 30 and 50 maybe, there we go, and a little higher for the y's. Let's just zoom it out. There we go, there's our data. So great, and it definitely looks like it falls on a pretty straight line. So how do we graph the regression line that models the data? Well, here's how we do it. So if I know it's a linear regression, I know it should look like a y equals mx plus b. My y is y1, my x is x1. So I'm not going to write y1 equals mx1 plus b. That's not quite, oops, I want the mx1 to be right, sorry. So see how everything ended up in the subscript there? That was a mistake. I need to, after the sub 1, I need to push the right arrow to get out of the subscript, and then equals mx sub 1 plus b. And that's to be like, what are you doing? You're crazy. That's because I don't actually have a line. What I want is, instead of using the equal sign here, I want to use the tilde symbol, which is the symbol that's like above the little accent thing next to the 1 on your keyboard. And that will give you the regression line, which is super cool, right? Like, and really, I didn't know you could do this until maybe 10 minutes before class. I was like, oh, there's this problem. Let's figure out how to do it. So I Googled, how do you do a regression in Desmos? And it was a 1-minute video showing me how to do it. So if there's something you want to do graphically and you think you can do it in Desmos, usually there's a video you can find that will show you how to do it pretty easily. So this tells us that if we were asked to find the regression line, our regression line would be y equals 1.88074 times x plus 82.6497. That would be our actual regression line. That is the line that is being graphed right here. And then question C, if an anthropologist found a femur bone of length 53 centimeters, how tall was the person? So I have not figured out how to enter in a data point so that it gives me the corresponding value, right? I was hoping it would spit out the value here. But what you can do is you can just look at your graph and be like, okay, I want to plug in 53. So let's see, 53 is right there. So there's 53, and we can click on the graph, and there it is. I got lucky. 53, and the Y value is 182.329. So if an anthropologist found a femur bone, whoops, I moved off it. If an anthropologist found a femur bone of length 53 centimeters, we would estimate or guess that the person was 182.329 centimeters tall. So kind of cool, right? I mean, I think it's kind of cool anyway. And then if we have time, we'll come back. That's problem 10 is totally different, not at all the same. I bet there's a way we could do problem 10 as well, but we will come back to that after we look at some of the other problems. So that should help you if you're in Guy or Lewis or Burke's class, do problem 4 on your group homework. At least in Guy's class. I assume everyone's gonna have groups, but I don't actually know if that's true. So if you're in Guy's class, he has asked you to form a group of like 4 people to do group work with. If I were in, I would select people I wanted to work with, maybe people in the co-class. If you know someone or want to get to know someone, you certainly could select someone in the class. So let's go ahead. I'm gonna stop sharing. And let's work on some of these problems because that's what we're gonna do. I have noticed over the years that of all the classes, the 17 series definitely feels like it covers a lot of material. So we are going to definitely I'm going to try to give you a lot of examples. And what I really need for you guys to do for me is to just let me know what you want to see. So if there are certain topics that you want to see in class next Tuesday, you should let me know before next Tuesday. Because I will definitely try to do examples that pertain to what is going on. If you have specific homework questions you want me to address, I can either address them specifically or do very similar examples if I feel like I shouldn't actually do the homework problem for you. But that said, let me know what you want and I will try to deliver that kind of material to you. All right, so yes, I have to be smart. So one thing I have to remind myself to do, which you guys unfortunately will not be able to tell me if I've done it or not, because you can't see what I am seeing here, is I have to remember to pin my video. So let me pin my video. Great, because that way, if you want to watch the recording later, you will actually see my video large as opposed to my video small. So that way you can actually see what I write on the board here. All right. So I'm gonna work through these practice problems, and if you have questions, either you can try writing something in the chat. I can't promise I will always see it in the chat, or you can unmute yourself and say words. That is also perfectly fine. I might jump. Occasionally students have said things that I've been like, oh no, so don't worry, it's okay to scare me. We're gonna have a fresh pen for class. So we're going to work through some difference quotient problems. It is important to be able to kind of simplify this type of expression because it's really kind of where the definition of the derivative is going to be coming from. So let's look at these first few problems. So I'm starting off with the function f of x equal to x squared plus 3x plus 4. And our job, by the way, how does that green pen look? Can you guys see that all right? So, yeah, that's what it kind of looks like to me. Oh, also, I should check let me check one of my video settings. Yeah, I think my green pen seemed better before. I will definitely use a different pen. One sec. I wonder if that would help. Let me ask you guys now. Is that any better? It's okay if it's not. Yeah, it's not great. Oh, it's better? Okay. So I guess that's good to know. So I turned off my adjust for low light setting, which means my face looks really dark, but my board is probably easier to read. And that's more important because it doesn't matter if you can see my face. It doesn't matter if you can see the board. But let's not use that pen. The problem is these pens come in 5 packs, and like 2 of the colors are great, and the other 3 colors are kind of mediocre. That's not true. Red's pretty.
I'm sorry. What problem are you doing on that page?
I'm doing problem 1A.
1A?
Yeah.
Okay, perfect. Okay, I see it. Thank you.
You're welcome. Come on, Patrick. All right, sorry. So we're looking at the function f of x equals x squared plus 3x plus 4. And we want to simplify the difference quotient, which is f of x plus h, f of x plus h minus f of x all over h. Now, what I really should point out here is that what we're doing is we're actually finding the slope of a line between 2 points, right? If you look at this function, which looks looks something like this, right? What we're doing is we're saying like this point here is x, comma f of x, and this point over here is x plus h, comma f of x plus h. And what we're doing is we are finding the slope of this secant line between them. So that's the whole idea behind this calculation, is that you're actually finding the slope of this secant line between these 2 points. So now I used up all the room on the side of the board. We'll use it as side of the board. So here's our function. And honestly, when I am calculating this difference quotient, what I usually like to do first is actually write out what f of x plus h is all on its own. So f of x plus h is just the same expression, except wherever I have an x, instead of having an x there, now I have what's in the parentheses, which is x plus h. And now we can go ahead and throw all that into this expression and try and see what we get. So f of x plus h minus f of x all over h is equal to this x plus h squared plus 3 times x plus h plus 4 minus f of x squared plus 3x plus 4. And it is super important that when you do this, you what's what I'm looking for? You make sure you're subtracting all of this part of here, so you just that when you subtract, you actually distribute the minus in there. So now we're going to simplify. So technically, this is a correct answer, right? We have written the thing we've been asked to write, but the question also says to find, to evaluate and simplify the difference quotient. So we definitely need to simplify. And here's the thing to keep in mind whenever you're simplifying a difference quotient. There's two things actually. The ultimate goal is to cancel out that h. That h in the denominator, we really would love for it to go away. And the intermediate goal we need to happen before we can get there is that all the things that don't have an h in the numerator need to cancel out. Sometimes that takes more effort than others, but eventually we almost always can make that happen. So here we need to multiply things out. X plus h quantity squared is going to multiply out to be x squared plus 2xh plus h squared. And then 3 distributed to x plus h is going to be plus 3x plus 3h plus 4. And then we have to distribute the minus sign. So we get minus x squared minus 3x minus 4. All over h still. And I should have an equal sign because these are equal. So now we can see that the things that don't have an h are going to end up canceling. X squared and minus x squared. 3x and minus 3x. 4 and minus 4. That's why it was especially important to make sure that we distributed the minus sign. If we didn't distribute it, then we wouldn't have things canceling like we know that they need to cancel. So then we're left with 2xh plus h squared plus 3h all over h. And some people at this point like to just divide each thing by h. I think that's fine, but I usually prefer to factor out an h from the numerator. This is going to be h times 2x plus h to the first plus 3 all over h. And then we can cancel this h and that h to be left with 2x plus h plus 3. So here's what this means. This means that we look back at our picture here, the slope of this line is 2x plus h plus 3, which obviously depends on what your x and your h actually are, right? If h was, right, h is the distance here between, and this is x, and this is x plus h, so this distance here is h. So if that distance gets bigger or smaller, the slope is going to get bigger or smaller. And if your x line changes, it's also going to affect the slope of the secant line. But the kind of the big picture idea here is that eventually we're going to use this piece of information to help us find the slope of the tangent line. So this is not the slope of the tangent line, this is the slope of the secant line, right? A line that connects 2 points of a graph. But eventually we will move on to finding the slope of a tangent line. Well, let's do more examples because it's definitely good to practice the algebra of this process.
So do we just leave it with that h, the 2x plus h plus 3?
So yes, but let me address the question that I think you're asking, which is that eventually, when we're trying to find the slope of the tangent line, we're going to use the definition of the derivative, also known as the limit definition of the derivative, to take the limit of this expression as h approaches 0. So what will happen is we will let h go to 0, and then this part will totally go away, and we'll just get 2x plus 3. So that's eventually where this is leading to. And we end at 10:20. So yes, we'll try not to go over. So let's look at this next one here. They do get more algebraically complicated. So our function now is x over x plus 2. And let's go ahead and write out what f of x plus h is. And I'm kind of a fan, a student actually taught me this, of wherever I have an x, just writing in parentheses. So parentheses over parentheses plus 2. You don't really need the parentheses here, but it's kind of a nice place where we'll be like, oh, instead of x, I'm putting in x plus h. It helps me make less mistakes. So then, the difference quotient, f of x plus h minus f of x, all over h, is going to end up being, it's going to be kind of gross. It's going to be, x over x, x plus h over x plus h plus 2 minus x over x plus 2 all over h. That looks kind of awful. It's okay. Sorry, what I want to say here. Yeah. So what I want to say is, that's what I want to say is this looks terrible. It's not so terrible. The problem is, to deal with this numerator, we have to get a common denominator. And the common denominator is not particularly nice. It's really just x plus h plus 2 times x plus 2. So there's a couple different ways to deal with this. The kind of easier algebraic way is to multiply both the top and the bottom by this common denominator. See how the orange looks. X plus h plus 2 times x plus 2. How's the orange? Can you guys see that all right?
Yeah, that
But I have a question.
Yes.
Like, so where did you get the f of x plus h equals x plus h over x plus h plus 2?
So I took my f of x, and wherever there was an x, I substituted in what?
Oh, x plus h.
Exactly.
Okay.
So now I'm going to multiply the top and bottom by this common denominator. The whole kind of goal here being that I want the denominators in, right, I hate fractions and fractions. The denominators in the numerator are going to end up canceling. So when I distribute this to the first term, the x plus h plus 2 cancel, and I get x plus h times x plus 2. When I multiply this by the second term, I get minus the x plus 2's cancel, so I get x times x plus h plus 2. All over h times x plus h plus 2 times x plus 2. And now we have to simplify, and hopefully everything that doesn't have an h on top will cancel. And then the remaining things that have h's, we can factor out an h and cancel this h on the bottom, right? That's the guy we want to cancel out. This other h in the denominator, we don't care about. It's this first h that started off in the denominator. That's the one that we need to make sure that we can cancel out.
So do we have to do both the top and the bottom of the whole like equation, or is it just for the numerator?
Sorry, I missed the very beginning of what you said.
So do we have to do for the entire equation that multiplication process, or is it just for the numerator?
No, we really have to do, so the thing is, when you're multiplying an expression by something, you're really only allowed to multiply by 1, otherwise you've changed it into something else. So I really didn't have to multiply the top and the bottom by the same thing. So then I'm really just multiplying by 1. Does that clarify things? Okay. So then I'm going to multiply at the top, which is, right, the algebra is always going to be kind of messy. It's just, that's why eventually we develop rules to make this process easier. But for now, the algebra is kind of like the challenging part. So someone's in the waiting room. Sorry, if I get scared, it's because noises have happened. So, welcome. All right. Cool. Okay, great. So, multiplying this out, I get x times x is x squared. X times 2 is 2x. X times h is xh or hx, either way. H times 2 is 2h. Minus, and then it's x times each of these things. So it's x squared, it's xh, and it's 2x. All over. I don't want to multiply at the bottom. There's nothing really to be gained by multiplying at the bottom. So then hopefully the non-h things cancel. Let's see. X squared and negative x squared cancel. 2x and negative 2x cancel. And xh and negative xh also do cancel. So sometimes some of the h things will also cancel. That's fine. As long as the not h things all cancel out. So I'm left with 2h, sure, over h times x plus h plus 2 times x plus 2. And then this h here can cancel out that h there. And then I've got 2 over x plus h plus 2 times x plus 2. And the reason I say that you don't want to multiply at the bottom is because eventually, if we're imagining that h is going to become 0, if this h becomes 0, then you've got x plus 2 times x plus 2, or x plus 2 squared on the bottom. So you don't want to multiply that out because usually it's easier algebra if you're actually taking the limit to let this part go to 0 and then simplify it after that. So don't multiply out the parts that don't need to. It's kind of a dumb thing to say, but what I want to say is don't multiply out the parts that don't need to be multiplied out, because we're going to learn that there are parts that are going to be easier after we've done letting h go to 0. Yeah. So let's look at the third one.
I have a question.
Yeah.
So How did you go from multiplying the top and the bottom to getting x plus h times x plus 2 minus x and all of that?
So when I multiply, when I multiply fractions together, I multiply the top parts together and the bottom parts together. The bottom parts I think are pretty straightforward, right? The bottom part is h times this, which is just h times this times this. When I multiply the top parts together, since there's subtraction here, I have to distribute. So I'm really multiplying this whole top part in orange, like this whole part here. I'm multiplying it by this part and by this part. When I multiply it here, the denominator there cancels with this factor here. So I really just get this x plus h times this x plus 2, which is exactly what I've got right there. And then when I distribute it to the second term, right here, then, so now the x plus h plus 2 is uncanceled, right? We still have it. And then when I multiply this here, the x plus 2 and the x plus 2, those cancel. And I'm left with x times x plus h plus 2. That's what's going on there. I will point out, there is another way to do this, which is a little bit messier, but the thought process is slightly cleaner. So let me point that out, just because it might help a couple of you see what's happening here. So where to erase? I guess I'll erase them. So another way we could have gone, which is going to look kind of gross, is by multiplying each thing by the thing we need to get a common denominator. Meaning, I could write this as x plus h over x plus h plus 2 times x plus 2 over x plus 2, and then minus x over x plus 2 times x plus h plus 2 over x plus h plus 2 all over h, which is a big old mess. But then we get the same sort of thing happening, right? I get x plus h times x plus 2, right? This part here is the same as this part here. I get x times x plus h plus 2, which is this part here, is the same as this part here. And then it's divided by x plus h plus 2 times x plus 2, which is this part here. And it's also divided by h, which is that part there. So it really is the same. It's just this is a little bit, not a lot. This is a little bit of a cleaner way of doing it. Okay. So these fraction ones are kind of simple, not gonna lie. Let's do another one. So let's look at problem C, 1C. So our function here is the square root of 2x plus 1. And f of x plus h, again, I'm just taking x and substituting in x plus h. So it's going to be the square root of 2 times parentheses plus 1, where instead of x in the parentheses, I'm putting x plus h. So then, my difference quotient, f of x plus h minus f of x all over h, is going to be equal to the square root of, I'm going to write this as 2x plus 2h plus 1. I distribute the 2 inside here, minus the square root of 2x plus 1 all over h. And now I'm kind of stuck, because I know I want the things that don't have h's to cancel out, but when you subtract square roots from each other, there's no like convenient way of doing that, right? There's no way to put these together as is. The only way to really deal with square roots subtracting one another is to multiply by the conjugate. What we're going to do is we're going to rewrite this as the same thing, square root of 2x plus 2h plus 1 minus the square root of 2x plus 1 all over h times, now really I have to multiply by 1, so whatever I multiply by on top, I also have to multiply by on bottom. So the conjugate of this expression is just the same thing, except you change the sign in the middle. So if two things multiplied together are subtracted together, I'm going to multiply by the same two things added together. So the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1 over the same thing. The reason for this is that when you multiply conjugates together, the middle term cancels out. So if I think of this as multiplying like a minus b times a plus b, what do I get when I multiply a minus b times a plus b? Well, I get a squared, I get plus a times b, but I also get minus b times a or a times b. And then I get minus b squared. And the middle terms cancel out. Right, that's a squared minus b squared. So whenever you multiply two conjugates together, you really just get the first thing squared minus the second thing squared, which is really convenient for us because we're going to get rid of the square roots. So what we're going to do here is the first thing squared minus the second thing squared all over the denominator, which is going to be just h times all of it. So h times parentheses square root of 2x plus 2h plus 1 minus the square root of 2x plus 1. And again, there would be middle terms, but the middle terms would exactly cancel out. So the middle terms would be this square root times that square root, and then minus this square root times that square root. And those exactly undo each other or cancel each other out. So now I'm going to do one of those teacher things that's terrible. I'm not going to write a new line because I don't have a lot of room. When you square a square root, you just get the stuff that's inside. So the square root of 2x plus 2h plus 1 squared is just 2x plus 2h plus 1. And the square root of 2x plus 1 squared is just 2x plus 1. Now I have to be a little extra careful here because it's still minus all of 2x plus 1. So there still should be parentheses around that. Sorry, that's some terrible glare. That's better. So then we distribute the minus sign. We get 2x plus 2h plus 1 minus 2x minus 1 all over h times the square root of 2x plus 2h plus 1 minus the square root of 2x plus 1. And then we can cancel the 2x's and the minus 2x, the 1 and the minus 1. And we're left with not a lot of room. I'm going to go up here if that's okay. We're left with on top 2h and the bottom h times the square root of 2x plus 2h plus 1 minus the square root of 2x plus 1. We can cancel this h multiplying into 2 and this h multiplying all the stuff. And finally, oops, I made a mistake. It's very small and easily fixed, but I did make a mistake. This was a plus and I accidentally changed it to a minus. That should be a plus. That should be a plus. That should be a plus.
Why does it have to be a plus?
Well, because the sign, the thing that I multiply on top by here has to be the same as the thing I multiply on the bottom by here. These have to be the same. And the reason it needs to be a plus here is because it's a minus here. So that when I multiply these together, it actually works out nicely. I'll come back to that. We're almost done with that now. But let me say, just in case it's not super evident what I'm doing. Right, this multiplication here of this thing times this thing on the top, just to make sure everyone's really cool with that. Here we go. So we multiply these together. I get this times this, square root of 2x plus h, sorry, the square root of 2x plus 2h plus 1 times the square root of 2x plus 2h plus 1. So here's an important thing to know. When you multiply a square root of a thing by a square root of the same thing, you get that thing. Yeah, exactly. So I'm just seeing the chats now. I don't always see this chats. Yeah, that is a good question, person whose name I can't see right now, Evelyn. The whole reason we multiply by the conjugate is to essentially deal with these square roots. There are other occasions where we might multiply by a conjugate, but it's mostly when you have like a square root plus or minus some other term. And they can both be square roots or a blend of them can be square roots. So if we multiply this times this, we just get this. It's like how if you multiply the square root of 5 by the square root of 5, you just get 5. This times this is not so nice. It's just the square root of 2x plus 2h plus 1 times the square root of 2x plus 1. And then this times this is minus the square root of 2x plus 1 times the square root of 2x plus 2h plus 1. And then finally, this times this is minus the square root of 2x plus 1 times the square root of 2x plus 1 is just 2x plus 1. And then if we look here, this term and this term are the same, right? It doesn't matter what order you multiply things in. 5 times 3 is still the same as 3 times 5. This times this is still the same as this times that. So this minus this, those cancel out. So that's why we multiply by the conjugate and why it has to be a plus sign here. So that if you have a minus here, it has to be a plus here and vice versa, so that we get this kind of thing happening. Whoops. So back to the problem. We're done pretty much, right? The h is canceled and we end up with 2 over the square root of 2x plus 2h plus 1 plus the square root of 2x plus 1.
I have a question. So for like, I'm just like going back to what you said. So like, since you're like kind of factoring it out, that's why you go back from like the plus sign to the negative sign again, or you go from, so you have like negative on top and plus on the bottom.
So what happened like from this step to this step here, I multiplied out the top and I just got what we got on the other side, right? I got this minus that. And on the bottom, right, I have a plus sign here. So I have h times all this stuff, and it's going to have a plus sign. Because this top part here has to be the same as this bottom part here. Because I'm really only allowed to multiply by 1. Otherwise, I'm changing the expression. Did that answer your question?
Yeah, I understand it better now.
Cool. Let's see, what time is it? Okay, we got 3 minutes. So I will just say, so most of these problems that we're doing, there are also solutions posted to them. So if you want to look at the solutions at some point, you're welcome to. I'm not going to do problem 2 because it's essentially the same problem, it's a different way. But I would encourage you to look at problem 2 on your own and kind of see how it looks the same, but it's a little bit different. But I do want to talk about problems 3, 4, and 5. Well, probably not all of them in 3 minutes, but I do want to look at those domain problems because domain is another thing that becomes an important topic to cover. So we'll just look at one of them real quick. Let's look at the first one. Maybe next week on Tuesday, we can talk more comprehensively about how domain works. So this function, f of x equal to x plus 3 over x squared minus 4, I want to find the domain. And in this case, the thing that we have to be concerned about is possible division by 0. So we want to say, well, I want to exclude where the denominator is equal to 0. And you might already see the solutions. That's fine. There's a couple different ways to solve this. One way is you could just factor. This does factor as x minus 2 times x plus 2 equal to 0. So we get x equal to 2 and x equal to negative 2. Another way to solve this is to bring the 4 over there and then take the square root of both sides. What's the square root of 4?
2.
Okay.
Minus 2.
Well, yes, you're getting to the crux of the problem here, which is what's the square root of x squared? And I'll tell you it's not exactly x.
Isn't it plus or minus x?
You're very close. That is the right idea, but it's actually the absolute value of x. And here's why. Pick any number you want for x. Like if I take the square root of 5 squared, what's 5 squared?
25.
What's the square root of 25?
Plus yeah.
Okay. What's the square root of negative 5 squared? Well, negative 5 squared is still 25. And the square root of 25 is still positive 5. So the point I want you to see is that when you take the square root of something squared, it always gives you the absolute value of that something. Right? The absolute value of 5 is 5. The absolute value of negative 5 is still 5. So it's actually really true that the square root of x squared is literally the same as the absolute value of x. It's kind of neat. So then, if you look at this equation and say, well, the absolute value of x needs to equal 2, oh, well, that means that x could equal 2, but x could also equal negative 2. So that's why we actually get plus or minus 2 as the solution here. So you don't ever need to do all this work when you're solving this. You can just jump straight from, oh, x squared equals 4 to x equals plus or minus 2. But this is really the reasoning behind why this works the way it works. Okay, I should answer the question, which is that the domain, we don't want 2 or negative 2. So we want everything but 2 and negative 2. Here's a number line. I know we're out of time. I don't want these numbers. I want everything else. So my domain is everything from negative infinity to negative 2 exclusive, union negative 2 to 2, exclusive with parentheses, union 2 to infinity. We always use parentheses for infinities because we don't include infinity because it's not a real number. And we're using parentheses on the 2 and negative 2 because we don't want to include them because we are specifically trying to exclude them. So that's how you would write the domain of this function. All right, we are out of time. I will.